All right, today we're going to look at some related rates. Now, in AP, related rates will actually be part of another question. You may not see a full question on related rates, but it could be a part A or a part D in another question that would involve a bunch of other things. And that's going to be typical this year, I'm sure, that any one question is going to start out and maybe have you do a tangent line and then drift into a Riemann sum and then maybe have a related rate at the end. Like, you're going to expect a little bit of everything in each question. But let's get started just really focusing on a related rate question. All right, we have water being poured in a conical tank that is 24 feet tall and has a diameter of 10 feet. So an inverted cone, very typical with AP. So one of the things we want to note here is that my height is 24 feet. Now it says the diameter is 20, so that means my radius is 10 feet. And we're going to write a formula for the cone in terms of h. Now we've done this in class a number of times. We always had to relate the height and the radius, and that is 10 over 24. So the formula itself for volume has way too many variables here, so we're going to eliminate that r variable. So if I cross multiply here, I get r equals 10 h over 24, or if we reduce, 5h over 12. So our volume is 1/3 pi r squared, so I'm going to swap out my r for the 5h over 12. That's going to be squared, and then we're multiplying by h. Let's clean this up just a little bit more. If I do everything on top, I'm going to square both of these, so I get 25, and then we multiplying by 1. So on top I actually get 25. I have the pi, and then I have h squared and another h, so I'm going to get an h cubed. Now I'm going to look at the bottom. I'm going to square this part, 144, and 144 times 3 is 432. So there is volume with respect to just h. So not a bad start here. Really just a little bit of algebra. Okay, there's my cone again. We want the volume of water is increasing at 3.4 cubic feet per minute, and the height of the water is 2 feet. At what rate is the height of the water changing? So this is our related rate portion here. So let's take that formula that we just had, 25 pi over 432 h cubed. Let's find the derivative with respect to time. So this becomes dv dt. I'm going to multiply this down, and we get 3 times 25 pi over 432. Now you'll always have your calculator with you, so don't forget about that. And we want dh dt. So there's our implicit differentiation with respect to time. Let's fill in a couple of the pieces that we know. So I'm going to fill in now 3.4 for the volume increase, and I'm going to multiply that part together, so I'm going to get 75 pi over 432, and this is the height of the water is 2 feet, so I'm going to put in a 2 here, square that, and dh dt. So now it's really just a calculator question. Let's do all of this here in my calculator and then divide that off. So I'm going to grab my calculator and punch all of this stuff in. So I'm going to get 75 times pi times 4, and then divide that by 432, and that gives me 2.182 3.4 divided by that answer. Sorry, let's go 3.4 divided by the 2.181. And I have dH dt is 1.558. Now this is going to be in feet per minute. Don't forget to put your units in here. So feet per minute. And with this, the radius of the surface of the water in the tank is increasing at 0.75 feet per minute. At what rate is the area of the surface changing when the radius is 4.2 feet? So they're actually doing a little switch now, because we're just talking about the surface of the water, which will have a circular shape. So now we're talking about the area of a circle. So area of a circle is pi r squared, and we want to know at what rate is the area changing. So we're going to take the derivative with respect to time. I'm going to move this down in front. This becomes 2 pi r dr dt. So let's substitute in. So dA dt, we're going to get 2 pi. The instant in time is 4.2 feet, and we're told that the radius is increasing at 0.75. So let's plug all of that into our calculator. 2 pi times 4.2 times 0.75, and I have the area is increasing at 19.792, and this is area. It's going to be square feet per minute. So there is a related rate question. Now it's very quick there. Let's see a different one. So here's another one. Looks a little more in depth. We have, first of all, a table, and then we have this picture of a pool. So this shows an above ground swimming pool. I'll let you read through this. So just stop this and read through it for a little bit. All right, so hopefully you've read through this. You see we have a chart that talks about the water being pumped into the pool. So that was our PT being pumped into the pool. And then they gave us another equation for a leak in the pool. And we saw this yesterday in a previous example about having two rates happening at once. The difference is now they didn't give us the equation for water being pumped in. They gave us this table up here about water being pumped in. All right, so the first part, not a related rate, it's actually a Riemann sum that we want to solve here using three subintervals of equal length and a midpoint Riemann sum. So we want to set up our rectangles so that we get a midpoint. So we're going to have to span all of that, and then we have our midpoint here. We're going to go this part here with the midpoint and this last rectangle here with the midpoint. So we're going to set up three rectangles to get our total amount of water that is being pumped in here. So our total volume of water being pumped in, we'll call that V, is the first rectangle, the base of 4. The height is the midpoint, so that's 46. And we're going to add on the base of 4 for the next rectangle. The height is 67. And then we have that base of 4 for our last rectangle. This height is 62. So now we're punching this all into our calculator, and I'm going to get 660 cubic feet of water that is being pumped in to the pool. All right, let's keep going. We're going to do B and C together now. We're going to talk first about calculating the total amount of water that leaked out. So in part A, we talked about the total amount of water that we added. Now we're going to use the R and get the total amount that had leaked out. Well, this is an accumulated rate. This is what we've looked at in a previous lesson. So I'm going to take the rate from 0 to 12, or the integral from 0 to 12 of that leak with respect to time. So I'm going to go to my calculator. I'm going to type in the 25 e raised to the negative 0.05 t, or x, and let's take the integral, second function, calculate number 7. Now, hopefully you guys, we've done enough of those that you can remember that. I'm not showing you my calculator. But I'm going to type in that integral, and I end up with 225.594 cubic feet of water that is leaked out over those 12 hours. All right, so that was B. How about C? Well, C, now we want to approximate the volume of water that's actually in the pool at 12 hours. So we've added some is leaked out. Now, remember up in the question that we were told that it contained 1,000 cubic feet of water at time 0. So when it started, there was 1,000 cubic feet of water. Now, over the 12 hours, we pumped in 660, but this leak has leaked out 225.594. So this is just a little algebra. Let's just add all of those together. So I get 1,434.406, but this says to the nearest cubic foot. Doesn't want all those decimals, so 1,434 cubic feet of water in the pool at this time. Now, so far we really haven't done a related rate yet, but notice in the question again, they give us the formula for volume. So I'm guessing, there it is in part D, we want to find the rate at which the volume of water in the pool is increasing at time equal to 8 hours, and how fast is the level in the pool rising at time equal to 8 hours. So we got a couple of things that we need to do here. So I'm going to first find the rate at which the volume is changing at time equal to 8 hours. So we're looking for dV dt. Well, this one really not a related rate. I'm not going to find this. I'm actually going to find it with my chart here and my R. So if I think about the chart, we're adding water at 60 cubic feet. I think it's per hour at this point. But we're also leaking, so I got to figure out how much we're leaking. So I'm using the PT that we added, and I got to subtract how much is leaking out at this particular instant in time. So I'm going to go to my calculator one more time. I already have RT in my calculator, so now I'm just going to go second function calculate. I need a value at 8 hours. And at 8 hours, RT, the rate of the leak, is 16.758. So subtracting those two, 60 minus 16.758, the rate at which the volume is changing, 43.242. Now I suspect that is probably going to be the hardest part of this particular question, just wrapping your head about how do I get it at time equal to 8. Now the next part isn't so bad. We are going to do our related rate. Using our volume formula here, I'm going to take dV dt, and this becomes 2 pi r dr dt, so the derivative of the first times the second, plus pi r squared dH dt. Now, we saw this in the previous example. There's a lot of different variables here. This one actually not too bad. Because it's a cylinder pool, the radius is actually never going to change. So this is 0. So that whole thing is gone. And I'm just looking at this second part now. I'm going to slide all of this up here. So now we're working with dV dt. We just figured out at 8 hours is 43.242. The radius of the pool is always 12. Let's figure out what is the rate of change for the height of the pool. And this is now a calculator. I'm going to take all of that and divide by 144 pi. So the rate of change in height at time equal to 8 hours, if I put all of that into my calculator, 43.242 divided off 144 pi, I have 0.0956. That would be feet per hour. Okay, again, don't forget your units. Okay, along with this, I posted some questions, so give those a shot.